Hello. Today I will show you how to fit a multiple linear regression in SPSS. We will use cherry data that contains 31 felled black cherry trees in Pennsylvania. The variables are tree diameter in inches, and height of the trees in feet. We also have volume of timber in cubic feet, which is the dependent variable in our example. First we draw a correlation matrix to see which variable is most correlated with the dependent variable volume. We go to Analyze, Bivariate Correlate and select all the three variables. We see diameter is the most correlated variable with volume. We also check scatterplot from Chart Builder. We select scatterplot matrix and pull all the variables. This will create a scatterplot matrix similar to the correlation matrix. We see there is no noticeable outlier in any of the plots. Dependent variable volume and independent variables diameter and heights have a linear relationship as indicated in the scatterplot. Now we try to fit a simple linear regression of the volume variable on the most correlated variable diameter. We go to Analyze menu and then Linear Regression. Here we choose volume as dependent and diameter as independent, and choose appropriate statistics that we want to see. We also select standardized residual versus standardized predicted plot, as well as histogram and normal PP plot of the standardized residuals. We see that the coefficients are printed in the output. We also see the histogram and normal PP plot. As points are in the 45-degree angle, we do not think standardized residuals deviate much from normality. However, in the residual plot, we can see that the plot is not random. A pattern of nonlinear trend is visible. To check the pattern, we can also loess at 75% of points. This will show the pattern of the points more clearly. Since this model does not satisfy our assumption of independence of residuals, we change the model. We add height in the plot and check the assumptions again. Even this model's residual plot is not much different than the previous one. As a quadratic curve is visible in the residual plot, we can try to add a polynomial term in our regression and try to see adding a polynomial term would help make the residual plot look random. For that, we compute a square term of the diameter variable from Transform and Compute Variable menu. We multiply diameter variable with the same variable and name it diam2. We also add an appropriate label and make sure the measurement scale is scale in SPSS variable view. Then we run another multiple linear regression of volume as dependent variable with diameter variable, its square as well as height variable as independent variables. When we check the independence of residual assumption from the standardized residual versus standardized fitted values, we see the nonlinear pattern is almost gone and this plot looks more random than the previous residual plots. Therefore, if we are satisfied with this residual plot, we can accept the current model as our final model. However, notice that this model includes a polynomial or quadratic term of diameter when a linear term of diameter is also present in this model. Therefore, from this final model, even though we have satisfied our assumptions of no outliers, model being linear in variables, residuals being independent, normal with mean zero and approximately constant variance, in the process we made it harder to interpret the coefficient corresponding to the diameter variable.